Hey, taking a break from making lots of plain cookies to talk to you guys about circles. So, on Tuesday, and I apologize that I'm getting to you a day late about this, we started talking about circles because you might choose to have a circle as the roof for the building that you're going to be making. So, I think circles are great because there's some really interesting mathematical concepts that you can talk about with them. But first, we need to make sure that we've got the vocabulary down. So, here's my very crappily drawn circle. And on the circle, there are a lot of things you could say. You could say that it has curves. You could say that it has a 360-degree angle. You could say that it has no sides. But right now I'm particularly interested in those things that you can measure in terms of distance with circles. So the first thing that you can measure is the distance around your circle. That is what we call the circumference. So circumference, I definitely want you to get comfortable saying that word. We had people coming up with lots of very different ways to say circumference. Circumference means distance around. It's a lot like our perimeter because it's around the circle. Then if you've got your distance around, you might also want to be thinking about the distance across. Now it could be going this way, it could be going this way. As long as you go straight through the center across the circle, you have the diameter. Diameter is our distance across. And then last, you have half of the diameter. That's if you just start at the center and you go to the border of your circle. That's what we call the radius. And today we're going to focus on circumference and diameter in particular, and the very special relationship that they have in any circle. No matter how big, no matter how small, every circle is going to have this relationship when you think about the circumference, or the distance around, and the diameter, or the distance across a circle. So in order to investigate this yesterday, you guys looked at several different circular objects, and you measured the distance around, and you measured the distance across. And then I told you to find the quotient. Take the circumference, divide it by the diameter. So we had circumference divided by diameter, and tell me what you got. And we ended up finding that we were around 3. No matter what circle you were working with, maybe you were like 2 point something, maybe you were 3 point something, but we were around 3. And if we were to do this more and more and be very accurate, and average everything over time, we would find that we would be getting closer and closer and closer to that lovely irrational number, pi. So, looks kind of like an N, looks kind of like a cursive R. It is neither of those things. It is pi, P-I, Greek letter. And pi is a number. It is approximately 3.141592, etc. And I say etc. because it is going to go on forever. It will never stop, and it will never repeat. So even the fastest computers that we have that are working on this have not been able to get more than a few billion decimal places. When you have a number like this that is not going to ever repeat and is not ever going to stop, you call that irrational. So pi is one of our favorite irrational numbers to consider because it has a special relationship to circles as well as some other things, but most of the time you're going to hear about it with circles. So that's pi. When we talk about approximating pi, I'm going to be okay with you stopping at the hundredths place and approximating to 3.14. So you could use 3.14 for pi. If you want to be exact, you can keep it as just pi. So we found that the circumference divided by the diameter was going to get us this number pi every time, at least if you go into the mathematical realm. When we were working with our measuring, we were a little bit off. Our measuring might have been wrong. We might have been imprecise in various places there. But once you get to an abstract mathematical circle, it is going to be exactly pi. Looking at this, you can use some fact family ideas to come up with some other equations. If I know that a product divided by a factor is going to give me one of the factors, then I also know that that same product divided by the other factor is going to give me the first factor. That would be like saying, if I had 6 divided by 2 equals 3, I also know that 6 divided by 3 is going to equal 2. So those two things are in that fact family. The nice thing about this is that gives me an equation where I have pi by itself. That gives me an equation where I have the diameter by itself. So let's make an equation where we have the circumference by itself. Well, 2, 3, and 6, another way they're related, 2 times 3 is going to give me 6. If I multiply my two factors, I'm going to get my product. So that tells me that in this fact family, if I were to take my two factors, pi and the diameter, and multiply them, I would get the product, which is the circumference. Using a fact family, we've got 3 equations that you can use. Let's say circle, fact family, to talk about distances around and across the circle. And the reason this is useful is because when we have a perimeter of a polygon, all we have to do is add up the sides. You know, like here I could just add my side lengths to get the perimeter. When we have a circle, that's not so easy because a circle doesn't have sides. Instead, let me use information that I can find, such as the diameter or perhaps the radius, and I can use that then to calculate the distance around that circle. So my circle fact family is useful. It gives me an equation for if I want to find the diameter. This would be useful if you did not know the diameter but you did know the circumference. It gives me an equation for the circumference. That would be useful if I did know the diameter and I did not know the circumference. And it also shows the relationship between these two quantities. You can probably see, just by looking at a circle, that the diameter is shorter than the circumference. Going just across the circle is going to be less distance than going all the way around the circle. What this tells us is about how much more the circumference is. If you were to unroll that circle, and you ended up with the circumference lined out like that, the diameter is only going to be about 1/3 of it. You would have to take this diameter and do it about 3 times, a little bit over, because this is 3.14 repeating, well, 3.14, etc. You'd have to do that diameter about 3 times to get your circumference. So the circumference is about 3 times longer than the diameter is going to be. So using this to make some calculations. If, for example, you had a diameter of 6 centimeters and you wanted to find the circumference, let's just start by finding the radius. If we know that the diameter is 6 going all the way across, then going just from the center to the outside is going to be half of that, so the radius is 3. Great. That's fairly simple. Thinking about the circumference, now we would use the equation where you know the diameter and then you can use pi to calculate the circumference. So I could say that c is going to be equal to 6 times pi. So if we write that as 6 pi, this would be the exact solution, 6 pi centimeters. But we could also approximate that. We could say that is approximately 6 times 3.14, and that would give us an approximate solution, which would be 18 point, I think 86? 84? 18.84, I believe, centimeters. Correct me if I'm wrong, I was doing that mentally. Checking to make sure that makes sense. Diameter is 6, that's across. This is about 3 times as long to go around. What if, on the other hand, we knew the circumference? Like, what if you knew that the circumference was 36 units long? Let's say 36 feet. Maybe it's in a yard or something like that. Well, the circumference is 36 feet, so the diameter should be about 1/3 of that. So that means that my expectation is that it's going to be around 12 feet. Let's get that exactly. Since I know the circumference and I want to find the diameter, I'm going to use c divided by pi equals d. So I could say 36 divided by pi. That is my exact solution. If I wanted to approximate that, I would say 36 divided by 3.14, and that's going to be approximately 11 and some change. I know it's 11 and a decimal. That's approximately 12 feet, so that tells me that I'm doing well. That matches what I know should be true. Then I threw some tricky stuff at you in the space race. I said, well, what if the circumference is equal to 8 pi? How are you going to find the diameter? People went about it a couple ways after looking at me and saying, I have no idea how to do this, it doesn't make sense, it's not pi, how can I use pi? So, first way, think about the circumference equation. The circumference is going to be equal to pi times the diameter, which you can switch using the commutative property, and you could say is equal to the diameter times pi. Comparing these two equations, I know that, well, if the circumference is circumference and pi is pi, the diameter must be 8. Another way that I could do this, so that's one way. Another way is if I chose, since I know the diameter, to use the, since I know the circumference, I could choose to use the equation where I start with the circumference and I divide by pi. So I would say 8 pi divided by pi. Well, yes, pi is a tricky number to use because it goes on forever and none of us know it all the way through, but any number divided by itself is always going to be 1. So if I do 8 times pi divided by pi, I'm going to end up just with 8 times 1, which tells me that, again, my diameter has to be 8. So whether you are approximating and using a calculator or using long division, or if you are using an exact form and thinking about how the equations are related, you should always be thinking, is my circumference longer than my diameter? Is it about 3 times as long? And in other words, is my diameter about 1/3 of my circumference? Tomorrow we're going to look at how this relates to area, because just like with polygons, where we needed to know the perimeter because we had to have 36 units, but we wanted to maximize space inside, here, as we're looking at our circles, we want to think about how we can maximize the space inside and compare that to those polygons. Have a good night.